Hello everyone, and once again welcome back to the Chem School. I hope you liked the last video on the classification of ligands. And in that, I specified that today I'll be talking about the bonding between the metals and the ligands. And in that, a very important bonding is the bonding between the metals and the metal carbonyls. Okay, so in this case, the effect that is generated is called as synergetic effect, or we will talk about synergic effect. Okay, so today the main topic that we are going to discuss is synergic bonding. So let's get started. Now, before we go to synergic bonding, let's understand some basics, okay? And that is how the bond formation is taking place between the metals and the carbonyls. Have a look at the first molecular orbital diagram. You have the metal, okay, with its orbital. Similarly, you have the carbonyl with its orbital. Now, in this case, if you have a look, you can see that this is axial bonds, okay, and they have the same charge. If this overlap, that is the metal orbital and the carbonyl orbital, if they overlap, you get something like this. And because this region, this electron cloud is between two nucleus and it is axial, right? Therefore, you will say that this is sigma bond formation. Okay, so this is very basic. So here, this electron cloud is formed between the two nucleus, and this is as simple. You can say that it is a sigma bond between the metal carbonyls. Okay, and which is going to be the strongest bond, of course. Okay, the next one. If you have a look at this molecular orbital, what is the difference that you can see? You can see the difference in the charge, that you can see, let's say, like this electron cloud are of similar nature and this electron cloud are of similar nature. Okay, that is what the charge is about. It is just talking about the nature. Don't take it as a real charge. Okay, similarly in carbonyl, you can say that this electron cloud is of similar nature and this electron cloud is of similar nature. So when two electron cloud of similar nature overlap, the bonding takes place. Okay, so in this case you can make out that this have similar nature, okay, and this have similar nature. Okay, but what is the difference? You can see that this, if overlaps, the electron cloud that is formed is above or below the nucleus. Okay, it is now lateral overlapping, right? Now this lateral overlapping is how it is happening in your pi bonds. Okay, but because of two different types of nature in the same bond, you will say this is pi star. Okay, so this is nothing but your anti-bonding pi orbitals. Okay, so that is depicted by pi star. Okay, so it means in metal carbonyls you will have two main types of bonding, that is, you will have a sigma bond formation and you will have a pi star bond formation. Okay, now let's see, if you mix them together, how does the picture look like, and that will give you a very clear idea about what is synergic bonding. Now have a look. I have drawn the metal orbitals and the carbonyl orbitals both together, that is the sigma and the pi star, that is the anti-bonding molecular orbitals. Now if you have a look at this, okay, what can you figure out? Just imagine if the electrons are going to overlap, how will your metal carbonyl complex look like? Okay, so now what is going to happen? The first, have a look at the axial positions between the metal and the carbon. Okay, you can see that this have similar electron cloud. I said don't take charge as, you know, hardcore thing that okay, plus charge will repel each other. Don't think about it. Just think that they have similar nature. Okay, so they will get along very easily, right? So what will happen is, in this you will have a sigma bond formation. So if they overlap, okay, the carbonyl in carbonyl the carbon has a lone pair of electron. Okay, and how do you know that? If you just draw the Lewis structure, what you will get is this. Okay, your oxygen has a plus charge, carbon has a minus charge. Is this clear? Fine. So because carbon has a negative charge, okay, and in carbon and oxygen, you know that carbon is less electronegative. So any species which is less electronegative and has a pair of electron, that will be a better electron donor. Okay, right? So in this case, carbon is having this lone pair of electron and that is getting donated to the empty orbital of your metal, that is empty d orbital, right? So now the carbon is donating this electron to the empty d orbital. Okay, and that will result in the formation of your sigma bond. Okay, now what happens in return? Now if you have this metal which has a lot of electrons, okay, excess electron, in that case what will happen? Metal will also donate an electron back to the empty orbital of the carbon. Okay, so the metal is donating its electron to the empty orbital of the carbon. It is pushing it back. Why? Because it already has a lot of electron. It also wants to get rid of some of them. Okay, so now when the metal push the electron towards the carbon, okay, the electron is going towards the opposite direction. Now this is giving electron and this is returning the electron back. Okay, so then you can think about the concept of back bonding. Okay, now this bonding is called as synergic bonding. Okay, where you are taking electron and the same metal is also trying to return some electrons to the original atom, that is carbon. So this is called as back bonding or synergic bonding, and the effect is called as synergic effect. Okay, now you know that this is sigma bond, and we know that, okay, this electron cloud and this electron cloud, okay, this will result in the formation of your anti-bonding orbitals. Okay, fine. So again I repeat, in synergic effect, what is happening, like we are talking about metal and carbonyls. In carbonyl compound, the carbon has excess lone pair which is getting donated to the metal, resulting in the formation of sigma bond. The metal has excess electron in its anti-bonding orbitals and the carbon has empty anti-bonding orbital. That is the reason the metal is donating its electron back, okay, from the anti-bonding orbitals to the carbon empty orbitals, that is anti-bonding empty orbitals. This effect is called as synergic effect, and the bonding here is called as synergic bonding or synergic bonding. As simple as that. Now, what are the important things that you need to remember? Okay, the first one, this effect will only take place when your metal, okay, is electron rich. Okay, I repeat, this will only take place when your metal is electron rich. Okay, the next one, the lone pair donor, which is forming the sigma bond, should have empty pi star antibonding orbitals. Okay, I repeat, the donor should have empty pi star orbitals. Okay, that is the second thing. Okay, so donor should have empty anti-bonding orbitals. Is this clear? Now, if this is true, then what will happen? Initially, if you check the bond order, between metal and the carbon, there is one bond, usually, okay? Then this bond order between metal and carbon is 1. And you can see that the carbon and oxygen has 3 bonds, so the bond order is 3. So now the bond order is 1 and 3, okay, when the sigma bond is formed. But when the anti-bonding, okay, orbital bonding takes place, overlap takes place in this region, what happens? Okay, something of this sort happen. This is your bond order. Your carbonyl bond, okay, because it has lost some electron, the bond order is close to 2. So carbon and oxygen will have 2 bonds, and there will be 2 bonds between the metal and the carbonyl. Okay, thereby this bond distance decreases and the bond distance between the carbon and oxygen increases, the bond length increases. Okay, so after the measurement of the bond length, calculation of the bond length, also you can find this changes. Is this clear? This change is because of synergic bonding. The next thing, what if the metal is not electron rich? Okay, it does not have a lot of electrons in its d orbital. What if the donor has electron in its anti-bonding orbital? Okay, let's talk about ammonia. Okay, ammonia has electron in its anti-bonding orbital. So what will happen? They will form sigma bond, but they will not form this pi star. Okay, that is the reason, if you check, the carbonyls are better ligands, okay, than the ammonia. Okay, this is how your question will be asked in your entrance. Okay, why carbonyls are better ligands than, or they form stronger complexes than your ammonia? The reason is the synergic bonding. Okay, carbonyl, because of synergic bonding, okay, you can have a look at the bond order. The bond is stronger compared to ammonia. Okay, and that is the reason that they are better ligands. Is this clear? So I repeat, if the metal is not electron rich and if they do not have empty pi star like orbitals, anti-bonding orbitals, then synergic bonding will not take place. Okay, and when synergic bonding does not take place, the ligand, the metal and the ligand bond is not going to be as strong as the other cases like the carbonyl. Is this clear? The next thing that I want to talk about is pi acids. Okay. Now in this case, have a look at this carbon, okay, and the metal. So in this case, the metal orbitals are d pi because the electrons are coming from d orbital d pi. And in this case, carbon is p pi. So this bonding is d pi p pi bonding. Okay, and when you have d pi p pi bonding, this p pi indicates that they are pi acids. Okay, this is what you will say, that they are all pi acids, but they are p pi acids. Okay, I repeat, because carbon has the last electron in its p orbital, so they are p pi acids. But if you have pH3, phosphine, okay, so in phosphorus the electron is in the d orbital, so you will have d pi like complexes. They are also pi acids, but they are d pi acids. Okay, small things, but you can remember that, and it is not quite difficult as well. Okay, so this was all. Let's have a quick revision. Now the question, most important question that is asked is, why is carbonyl a stronger ligand than ammonia? I said the answer, because carbonyl can form something called as synergic bonding or back bonding. Okay, why? We said because it fulfills two important conditions. That is, for synergic bonding, you should have metal that should be electron rich. Okay, and the second thing is that the ligand should have empty anti-bonding orbitals. Okay, next. Now, in this case, when the synergic bonding takes place, you will get pi acids, and they are also called as pi acceptor ligands. They are of two types. Usually you will have either the electron which is going in the empty p orbital, or the electron, okay, is going in the empty d orbital. Okay, we are talking about the anti-bonding orbitals. So for p orbital, these are the examples, and for d orbital, these are the examples. You can have more. Now the fact that the bond order is changing is from this. You can see that in carbonyl, after the back bonding takes place, the bond length changes, or it increases from 1.128 angstrom to 1.15 angstrom, thereby indicating that in carbonyl the triple bond is moving towards double bond character. Okay, so this was all about metal bonding. Okay, I hope you are very clear with all this concept. If you have a doubt, do ask me in the comment box. See you soon in the next class. Thank you.